Let's now look at equilibrium and free energy for a chemical reaction. Sometimes a system can achieve the lowest possible free energy by going to equilibrium, not by going to completion. So in the first instance, this would be a complete reaction. Sliding down the hill, the lowest point would be right there. But in an equilibrium reaction or a reversible reaction, going to completion might not give you the lowest energy. Instead, being somewhere in the middle will. So again, the equilibrium point will occur at the lowest value of free energy. So things will settle at equilibrium right there. There's a formula on your data sheet, and it looks like this. And this K, that is your equilibrium constant. And this equilibrium constant could be a KSP, or it could be just a general KC. But remember all the rules for equilibrium, and now we're just applying it to our free energy. So remember, if you have coefficients balancing an equation, they become exponents. You also can use Q instead of K. So if you had a situation where if you didn't know if it was at equilibrium or not, you could also use a Q. And this is where we use that very first value of R. So that R that's listed with the R that we use with our ideal gas law with PV equals nRT, this is the R that is listed first. And so this goes with thermodynamics. The reason why it goes with thermodynamics here is because the units are in joules. When we're looking at the temperature in this formula, make sure that you're in Kelvin. Let's look at this reaction and figure out if it is thermodynamically favorable at standard conditions. So we have our balanced chemical equation here, and then we were given our delta H values and also our entropy values. So what I'm going to do is I'm going to have to do products minus reactants so I can find delta H, and then I'm going to do the same to find the entropy. So there's my formula, and I can go ahead and put those numbers in and solve products minus reactants. And let's do the same thing for delta S, and I get a negative 198.3 joules per mole per Kelvin. So let's put this in our Gibbs free energy equation. Remember to change the joules to kilojoules to put into this formula. And I get a negative 33.3 kilojoules. So is it thermodynamically favorable at standard conditions? And the answer is yes. And that's because my delta G is a negative value. Now calculate the value of the equilibrium constant for this reaction under standard conditions. So I'm going to use this equation, and then this is my delta G from what we just figured out. And remember, when you're using this reaction, your R is going to be the one that has joules in it. I'm going to get my natural log of K on one side all by itself. So my answer is a positive 13.4. And to get it out of the natural log, I need to raise it to the e power. So my final answer is 6.9 times 10 to the 5th. Notice that this is very, very large. So even though it's our equilibrium constant, because it's so big, we would assume that it would go to completion. But this is what's going to happen. If your delta G is negative, then you're going to have a very, very large K. So this will be product favored. It's going to make lots of products. That's what thermodynamically favorable means, is that it makes lots of products. So you would correlate that you would have a large K. And we get that here if we look at a table that is looking at delta G's with equilibrium constants. You can see that when you have a positive value, then you end up with a very, very small K. So in other words, it's reactant favored. And if you have a negative value of delta G, then that correlates with having a very, very large K, or being product favored, or making more products than reactants. Just a review of equilibrium. When Q is less than K, so this would be an experimental data to see if we're at equilibrium. When your Q is smaller than your equilibrium constant, then the reaction will proceed spontaneous towards the right until the equilibrium is achieved. When your experimental Q is larger than K, then the reaction will proceed spontaneous towards the left, making more reactants until equilibrium is achieved. And when you have your Q is equal to K, then that means that you are already at equilibrium. Let's do another problem that has this free energy formula with the equilibrium constant. So we're given our free energy, and of course we know that we're going to use the R with the joules. And it says, what is the K at 25 degrees Celsius? So remember with these, we need to be in absolute temperature. So I'm going to add 273. So this is 298 Kelvin is the number that I will use. So let's go ahead and use our formula, and I want to get my K on one side. So the natural log of K is going to equal to my delta G over negative R times T. Put in our values, and I'm going to have a positive number. My natural log is going to be equal to 5.49. And to get rid of that natural log, take everything to the E. And I get 242 as my number. Remember, there's no units with equilibrium constants. And so what does this number tell us? Is it products or reactants favored? And it is products favored. So there's going to be more products. So with having a delta G as a negative, you would expect to have more products. Here we have the dissolution of two solids in water, and we have sodium chloride and we have silver chloride, and we're given their delta H's and their delta S's. So let's find the free energy and also the equilibrium constant for each reaction. So let's do our sodium chloride first. When I put my numbers in for the sodium chloride, we get a negative 9.3 kilojoules as our delta G. So we know that this will be spontaneous. Let's go ahead and do the next one. And when I calculate and put the numbers into our formula, we get a positive 55.5 kilojoules. So this is not thermodynamically favored. Silver chloride is typically a precipitate, so it doesn't dissolve in normal conditions. And this is the calculation that shows this. Now let's find our KSP for each of the reactions. So I'm going to just clear my slide, start with the formula, and I'm going to rearrange it to put the natural log of the equilibrium constant on one side. And working out the math, I have the natural log of K is equal to 3.75. So put this to the E, and I get 43. So this is product favored. I do have a negative value for delta G, so I would assume that my K would be larger than 1. So now let's work it out for the silver chloride. Start with the formula. This is for the silver chloride. Put the natural log of that KSP on one side. Put our numbers in. And I get a negative 22.4. So put that in the exponent of an E. And my KSP of the silver chloride is 1.9 times 10 to the minus 10. So we can see that this is very reactant favored. Our delta G is positive, so therefore our equilibrium constant will be very small. So again, we can see the correlation. If you have a thermodynamically favored reaction, then that means that you're going to have a negative delta G and you will have a larger K. And if you have a non-thermodynamically favored positive delta G, then that means you're going to have a very small equilibrium constant. And this makes sense. We've seen this in the lab that table salt will dissolve in water at normal conditions, but the silver chloride won't. It typically is a precipitate, so we can't get it to dissolve very much. Suppose that a certain chemical reaction has a large value of K and a negative value of G. Will the reaction rate be fast or slow? And explain. So be careful. Even though we know that it is product favored, having a negative delta G and a large K, we don't know the rate. So it might be over decades or seconds, We just don't know. So you can't tell how fast a reaction goes by this thermodynamic data. We just know that it will proceed and make products. And it all has to do with your activation energy. So in this first chart here at the bottom, this has a very high activation energy compared to its neighbor. And so we know that this one is going to be slower than this one. This one's going to be faster, just because the activation energy is shorter. So again, thermodynamics tells us nothing about how fast things go. It does tell us what direction it will go and if it will proceed from reactants to products. What happens if you have a non-thermodynamic reaction and you need it to happen? You can add electricity. Electricity can cause a practice to occur that is not normally favorable. So an example of this is charging a battery. You add some electricity and this can cause the chemical reaction to go forward and make products. Also electrolysis. So this might be plating a metal on another metal. You again are going to provide some electricity to make the reaction happen. Also, light may be a source of energy for driving a process that normally would not occur. So a good example of this is the photoionization of an electron in an atom, or in photosynthesis, the conversion of carbon dioxide into glucose. All of these use light to drive the reaction. And then a very common thing found in biological systems is called coupling. And this is where you group thermodynamically favorable reactions with the unfavorable. An example of this would be conversion of ATP to ADP in cells. And you end up grouping a thermodynamically favorable reaction with one that is unfavorable. And so the one that is favorable, it can drive the reaction and cause that there is enough energy for the non-thermodynamic one to occur. So let's look at this coupling. Looking at the reaction at the top, I see I have some copper 2 sulfide, and we are getting the element copper from this compound. And notice that it is not a thermodynamically favorable process because my delta G is positive. So how can I get the copper from my copper 2 sulfide? We can couple it with this reaction. So this reaction where we burn sulfur in oxygen has a very negative delta G. And so if I combine the two, so I add the two equations to get an overall equation, I see that if I combine these or couple them together, I can make it spontaneous for both of them to occur. So now it is favorable to obtain that copper from that copper 2 sulfide. Here's another picture that shows this. So again, spontaneous and non-spontaneous are the old terminology. Spontaneous means thermodynamically favored. So we see if A goes to B plus C, my delta G is negative. And so that should happen with no outside intervention. But the second reaction is not thermodynamically favored. It's going to favor reactants. And so what will happen is if I pair these two together and I add them up, I get a negative 2 kilojoules per mole as my free energy, which is negative. So that's enough to drive both of the reactions so that they will both work. In this slide, we see how ATP provides the energy to be able to couple these two molecules together. And we see that in the second process, it is not thermodynamically favorable. But because I'm coupling it with this ATP to ADP reaction, I get overall a free energy that's negative. So this is enough energy to drive both of them.